An American household is typically delivered two physical goods as utilities. The first is water, and the ability to turn on a tap and reliably have fresh, clean water year-round, no matter recent precipitation, is
Yeah, this is one of the things that I'm excited about as part of this video is as an American, I don't really think about how I get various utilities to my house. It just appears. I turn the faucet, water is there. I turn my stove on, there's gas. I turn the lights on, there's electricity. I don't really think about this all that often. And again, my background being more from the software and tech space, I often think more in theoretical scenarios and in computational units and all that other jargon. I don't really think about like how do actual wires and lines and pipes get moved underground into my house so that way I can have access to all these things. So I'm interested to learn more about this myself.
undoubtedly impressive, but a water utility is typically a fairly local service. Except in a few fascinating exceptions, water tends to be gathered from a natural source, processed, and delivered to households fairly nearby. It's a fairly intuitive, fairly straightforward process that has been going on in some form for hundreds, even thousands of years. Natural gas, though? That's a modern marvel. The general rule across the world is that natural gas production happens where people are not. This is in part a happenstance of geography, in part the consequence of an aversion to proximity to production, but what it means is that gas often has to travel hundreds, if not thousands of miles to get to its end user. To get low-density, flammable gas across an entire continent is far from easy, and it's even harder to do so profitably. Whereas gasoline and other liquid fuels are dense enough that the cost of transport to the end user by truck is marginal relative to the overall cost, the same is not true for natural gas. Therefore, through time, what has turned the previously worthless gas into a profitable commodity was figuring out how to make the transport economics work. And the answer
Well, curious about that already. So you mentioned how dense gasoline is made it easier. I'm not really sure if I'm following that logic. Obviously, things that are heavier would theoretically mean that it costs more to transport. Maybe they just mean the means of which it is capable to transport these things, like gasoline being more dense, you can pour it into another container easily. Whereas gas, obviously, you have to figure out how do you physically have basically like an airtight system such that you can start transporting it all that way. But I'm curious if they'll actually cover why you couldn't just put the gas into a truck, and while it's lighter, it would be even easier to transport than something that's heavier. But maybe they'll cover that soon.
for that was pipelines. Really, really long ones. Taking the example of an end user in Basalt, Colorado, their town's local network hooks up to a larger transmission pipeline that follows the area's highway down the valley until around here. Under this golf course, this dead-end offshoot connects with the long-distance transmission pipelines spanning across Colorado. Now, the fact that this happens under a golf course demonstrates something important. The pipeline operator does not own the land through which the pipeline passes. Rather, they own the right for the pipeline to pass through others' land. They own an easement. When a pipeline is constructed, the company negotiates with landowners to purchase the easement, or if negotiations don't go well, acquires it through eminent domain. In exchange, the landowner gets paid a lump sum more or less equivalent to the reduction in property value caused by the new easement. After all, the property value will be lower. Not only will buyers be wary of living near a pipeline due to the low but non-zero risk of an accident, but easements also come with restrictions on what one can do with the land. Typically, you can't build any buildings, you can't plant any trees, you really can only have pavement, grass, or dirt. The operator needs to be able to access the pipeline for maintenance and repair at any time, so they can't have a permanent structure in the way. And these easements are legally binding for eternity. They are baked in with a property's title, so buyers must still.
Wow, that actually sounds like a pretty bad deal for individual owners. Though I see why this would be beneficial at a societal level. Obviously, each of us individually do not like the idea of pipes running under our homes or under our properties because exactly those reasons that they highlighted. The property is less valuable, there could be risks. It also prevents you from fully utilizing the space that you own. And so I would suspect most individuals would just say no if this was brought up as an opportunity. I think we see a similar issue for the housing crisis in general. When certain regions in America are discussing whether or not you can add more multifamily homes, things like that, the local residents who have lived there for a while and have homes there are the ones who are fighting against this because they don't want their property values to decrease, even though they might agree philosophically that there should be more housing for people so that way they can live and enjoy their lives too. But it's a not where I am type of mentality. And so, as a society, if everybody said this, nobody would agree, and then we wouldn't have these utilities or gas or other things that other people need for the betterment of everyone. So, it is interesting, but this dichotomy exists where this trade off has to be made at some level, and somebody has to be on the losing side, for lack of a better term, in small individual cases, so that way we win collectively.
Abide by the restrictions agreed upon by the original seller. Here, the adjacent housing development is laid out in a way to avoid the largely invisible right-of-way. Then on the other side of the river, the right-of-way slides between buildings, barely even.
It might be more fair, as I think about it more, for these easements maybe to be more like leases of some sort, especially because if you're expecting to have them forever and the property is technically owned by that other individual, it might be more fair to say, like, we're going to pay you rent, quote unquote, for that property. And that might be more fair than saying, like, we gave you this payment, who knows when, like 100 years ago, to maybe even a different owner, and now you inherit that property and you have no say over that existing there. That might be one way to make that a little bit more fair, but we might be getting off topic here.
Visible from a satellite view. But as the hills start, the right-of-way takes its more typical form. A 50-foot wide stretch of land devoid of trees. And that lack of trees originates, of course, from construction. That process is fairly straightforward. First, heavy machinery is used to dig a trench. Then, sections of pipe are laid out next to the trench, and a pipe bending machine comes through to bend the pipe to follow the topography. Next, these shorter sections are welded together into longer sections, and the welds are strictly inspected. After all, structural integrity is critically necessary to prevent an incident. Once complete, they'll place these long sections in the trench on sandbags to prevent damage to their protective coating. Then soft, rock-free dirt is placed to directly surround the pipe, followed by the previously removed dirt to fill the rest of the trench. From there,
I'm not too familiar with this channel. Just from their use of terminology and how they're describing these things, I'm not sure if they are from an engineering background. Maybe I'm being presumptuous here, but we've actually covered videos from other civil engineers, for instance, and they use far more technical jargon, for lack of a better term. And so they really get into the specificity of how some of these things are being traded off, whereas this individual is just saying dirt without rocks is making me skeptical. Maybe they are intentionally trying to use more everyday language to be easier for a variety of audiences, but I've been noticing this so far in this video. Maybe they'll switch that up. Maybe if any of you are familiar with this channel, let me know. Maybe I'm wrong here, but I'm already curious as to how they're describing how this works and the development here in these terms for them to have been an engineer at some point.
crews test the pipe by filling it with water and pressurizing it well beyond its normal operating pressure, and that's about it. Pipeline construction is relatively straightforward and moves relatively fast. Under the right conditions, crews can install upward of a mile of pipe a day.
Maybe I'm picking on this individual, but again, I don't think I've ever heard any engineer ever say the phrase, "It's pretty straightforward, relatively easy." You could ask an engineer to like get a piece of paper out of a notebook and they'd be like, okay, well, first off, there's many risks that are associated with this. I could accidentally try to pull on the piece of paper and the notebook could go flying. I could get a paper cut. I could rip out multiple pages instead of just one page. Like, the standard engineer would probably be adding so many caveats to this, or maybe those are just the engineers that I'm familiar with. But again, I don't think I've ever heard any engineer just say, yeah, it's easy, just like that. You just link up the pipes, easy peasy, you keep going on. Seems odd to me.
Often across quite remote environments. But there is more to pipeline construction than just constructing the pipe. After all, if you put natural gas into a pipeline in Texas, it doesn't just magically flow to Colorado. That's why you need this, a compressor station. As the name implies, these are the facilities that compress the gas, and it's this pressure that propels the gas forward through the pipeline at a speed of about 25 miles or 40 kilometers.
So this is interesting. This makes sense. As a similar system that I'm familiar with, that I know that I haven't actually interacted with personally, but if you come from a software engineering or computer background, something we learned and had to discuss, and even at some point, probably in college, had to run some calculations over, is when you transfer data over lines, basically you lose the electricity or the signal, whether it's analog or digital. And so you basically need like repeaters or something that is enabling that signal to continue through, or amplifiers or something along those lines, because you can't just have like a single cable that goes from like America to China and you just start typing away and it just picks it all up and everything's good to go. There's only so far that it can transmit naturally. So this makes sense to me that the air, as you push it through pipes, would basically lose pressure over time as you have this kind of larger expanse. And you might have some areas that are higher pressure and some that are lower pressure. And so you need to compress it again so it can keep going on its way and keep being moved efficiently.
Per hour. But they're also important for making the economics work. An average household uses about 200 cubic feet of natural gas a day. That's a lot of volume of gas. It'd fill up a 6-foot or 2-meter cube, or the volume of about 10 fridges. The economics of transporting this gas would never work if it were done at its natural density. That's why they compress it. Quite a lot, in fact, between 500 and 1,400 pounds per square inch, allowing a pipeline to be used far more efficiently. These compressor stations are also often home to so-called pig launchers, which are more humane than they sound. That's because these are what are referred to as pigs, devices placed into the pipeline to perform some function. Some pigs clean the pipeline, whereas others are smart pigs fitted with sensors to inspect it for any vulnerabilities. While less relevant in natural gas pipelines, operators will even use pigs to separate out two different products moving through a pipeline.
Yeah, this scenario stands out to me. Again, maybe I'm picking on this individual too much, but I can't imagine anybody is using the term pig in a more serious engineering practice or area where you're trying to discuss sensors and cleaning out these pipes. I assume this is something that maybe the standard individual, maybe the people who actually put them in, would be discussing, but likely not somebody who actually architects or prepares these pipelines or is in charge of these facilities.
They might send a batch of traditional vehicle fuel, then a pig, then a batch of jet fuel, for example. And wherever there's a pig launcher, there's also a pig catcher that's able to remove.
Though I have to admit, it is very amusing for them to be saying pig and pig launcher and pig catcher. This does seem like it would be fun. On the opposite end, I would have to give them credit. If I had something that I could describe everything as pigs all the time, I probably would do it, even though I know that's not the appropriate term for it. So I'll give them some credit there.
Move the device from the pipeline while still allowing product to flow. Now, this pipeline eventually emerges from the mountains into another golf course, this time just south of the town of Eagle. From there, it connects to another pipeline. Right continues east, but left eventually dead ends just a few miles down the road. This is common because while one major category of customers for these long-distance transmission pipelines is the local utilities that distribute gas to local users, the other big customers are large industrial facilities that use so much natural gas that they have a direct connection to the long-distance pipelines. In this case, it's a plant that turns gypsum mined nearby into plaster drywall, and it's energy intensive enough that the facility operates its own 6-megawatt natural gas power plant. The rest of the pipeline, though, more or less follows the path of Route 6, then diverts south over a set of hills before reconnecting with the highway and ending up here, another compressor station. Although this compressor station isn't operated by Black Hills Energy like the pipeline up until this point. It's operated by Xcel Energy. That's because here, the pipeline's ownership changes, which is also abundantly common. Pipelines in the US are highly regulated by the Federal Energy Regulatory Commission, and as part of that, interstate pipeline operators are required to provide non-discriminatory open access to all qualified shippers. Effectively, they're not even allowed to provide preference to their own product. FERC also regulates rates. Black Hills Energy, for example, is allowed to charge $36.87 to reserve a decatherm of pipeline capacity during the winter when demand is higher. That guarantees capacity, then they'll charge another 10 cents per decatherm for the actual transmission. Alternately, shippers can pay just 94 cents per decatherm with no capacity charge for interruptible transmission, where product is shipped only if there is available capacity. The fact that the system is open access is ultimately how a product can find its way through the nation's web of pipelines all the way from where it's produced. A shipper might pay a dozen different companies for their transmission service to get the gas from its origin. And in the case of an end user in Colorado, it's quite likely that the origin for its gas is here, Texas's Permian Basin. There, the natural gas is extracted from the ground and processed into its commodity form. The area's primary industry is the more lucrative oil production, but natural gas is often a byproduct of that. Still to this day, many rigs burn off natural gas if they lack the infrastructure to divert it for sale, but an increasing number do capture both. But whether extracted via combined or dedicated rigs, it is often difficult to fluctuate production quickly to match demand. And demand fluctuates wildly considering so much of the use of the gas is for heating. So that's the role of these 400 different natural gas storage sites dotted across America. Some of these sites are just the very areas where gas was previously extracted from, depleted underground caverns. Once all of that original gas is gathered, the giant Swiss cheese holes in the ground, sometimes spanning thousands of acres, sit empty, and that makes them ideal for storage. They also already have existing wells, existing extraction and injecting methods, and existing pipeline connections. Here, gas is reinjected into the impermeable natural caverns some 1,000 to 5,000 feet or 300 to 1,500 meters below the ground, where the working gas, the natural gas that is commodified, occupies the upper part of the cavern and a cushion gas maintains a pressure buffer at the bottom. Because the depleted natural gas fields are established, proven, and widespread, their geology and infrastructure makes them the most inexpensive and easiest way to store natural gas. There is, however, another method that crept into more use about a decade ago as the country ramped up some storage.
So it's interesting that they actually reuse the areas in which they might have gotten natural gas from the past. They highlighted this cushion gas existing. They didn't really explain why that was there, so I'm just going to assume that maybe it's for avoiding situations where there's like other air pockets or something like that, and so they inject a denser gas. So that way the natural gas that they're using for consumption is higher up, and then maybe this forces out other types of gas or air that is less dense. And so that way when you go to pull up the gas, you get the one that you're looking for. But it's unclear if that's exactly the reason. They just really brushed over that very quickly.
Storage capacity. Salt caverns, which can quickly turn over storage since they can accept a higher ratio of working gas to cushion gas. Leaching out and creating salt caverns is expensive, but because of their high withdrawal and injection rates, which can cycle up to 12 times per year, that cost can be justified. The short withdrawal cycle is ideal for pumping energy into power plants during peak periods, and because more natural salt caverns are found in the South and Gulf area, this is where they're increasingly being put to use. The third type, similar to depleted oil fields in structure, are drained aquifers. These share the characteristics of being underground natural storage areas, but because they previously stored water, the surfaces can be permeable and the caverns less explored. It's more expensive to transform aquifers into natural gas storage, so it's primarily done in areas like the Midwest, where depleted oil fields are less common. Furthermore, aquifers require up to 80% cushion gas, meaning the amount of working gas they actually hold is far less than something like a salt cavern, making injection and withdrawal more difficult. But not all the gas extracted in Texas, or anywhere in the US for that matter, will even be used in the US. Increasingly, gas is not only transported across a continent, but across the world. And to get to such far-flung markets, it's moved as a liquid, crossing oceans, gulfs, seas, and straits in one of these. This is a QMax class liquefied natural gas carrier. There are 14 of them worldwide, and their classification signals that they are the very largest vessel capable of docking at Qatar's LNG terminals, making them the largest LNG carriers in the world. But in terms of sheer capacity, these are small in comparison to their conventional oil tanker contemporaries. A QMax can carry some 266,000 cubic meters of liquefied.
For some reason, I just feel like the background music is like a little intense. Like it's very subtle, but it's like this rhythmic beating that keeps existing here. I feel like it's in like a movie where like a serial killer is about to turn the corner or something, but for some reason we have it on for this segment where they're just showing these boats that exist. So I don't know, I feel like I'm getting a disproportionate feeling as I'm observing this than what I would expect.
Natural gas, whereas the world's largest TI class supertankers can carry up to 450,000 cubic meters of oil. And yet, these conventional oil tankers, with their superior storage, come at a fraction of the cost of an LNG carrier, as the last TI class supertanker cost $82 million in 2003, whereas a QMax runs in the $200 to $300 million range. While smaller, more expensive to build, and more expensive to maintain given the requirement of keeping natural gas in a fluid state, experts believe that there will soon be more LNG tankers plodding across the oceans than oil tankers. The reason as to why has to do with some geography and some physics.
So maybe they'll get into it here, but I was fairly certain we started earlier in the video where they were highlighting how easy gas was to move because it was denser, and that it just didn't make sense to transport it in a similar fashion. And then here we are basically using the exact same paradigm, but over water, and suddenly it's becoming such a great way to transport natural gas. I'm not really sure if I'm following the rationale for it. It could just be over the water, it's just easier to transport it this way than piping, whereas once you get a pipe in, you can just keep transporting as much as you want continuously. But I hope they explain that a bit, because we seem to have completely brushed past it when we were referring to tanks and them being driven as completely ridiculous as an option. But here we have a boat acting as a tanker, carrying the exact same thing, and here it makes so much sense. I'm not sure if I'm following that.
Global scale, the demand for natural gas is in places far from the supply. In 2023, these three countries were the largest LNG importers in the world, with China narrowly outpacing Japan. For decades, these three countries have been at the top of the list, with Japan the world's #1 year in, year out until 2021. And
that is interesting. I wonder if they're going to explain why they use this so much, and why like these three countries, China, Japan, and South Korea, are outpacing everyone else. They don't have the other countries on this visual, so it's hard to tell how far off the other countries are, but that is very curious, especially considering Japan is a fraction of the size of China.
For two of these three countries, total consumption exactly matches or very nearly matches imports. Put simply, Japan has a very limited natural gas, and South Korea has almost none. And while China does have a strong domestic supply, it cannot nearly keep pace with its own demand. The difficulty is, most of the big suppliers are far away and across oceans that make any sort of pipeline project infeasible. So geography has dictated if natural gas is to get from the US or Qatar or Russia or Norway or Australia, it's likely going to be by ship. But it's physics that make natural gas cost competitive. For natural gas to enter a liquid state, it needs to be cooled to and kept at -260 degrees Fahrenheit or -162 degrees Celsius, which is what makes LNG ships so expensive to build and expensive to run. But it's worth the trade-off because once cooled into a liquid, natural gas shrinks to 1/600th of its previous volume. While natural gas has been lobbied as a cleaner, more efficient energy source by proponents, it's really this incredible transformation from voluminous gas to energy-dense liquid that makes this energy source so remarkable and now so important on a global scale. By keeping the gas at -260 Fahrenheit, the common adage goes, a beach ball's worth of gas shrinks down to the size of a ping pong ball. But that example lacks scale. Phrased in another way, that a single ship's worth of LNG becomes 600 ships worth of gas in its natural state, it becomes easier to understand why LNG has skyrocketed in trade volume decade after decade, even if it's incredibly expensive and labor-intensive to keep the stuff at such a cold temperature. Before liquid natural gas can be loaded onto an expensive boat, it needs to be cooled down at an expensive liquefaction facility. At each liquefaction facility, there are what the industry calls trains, where the gas is treated to remove impurities, then progressively cooled to turn raw gas into clean gas, then clean gas into liquid gas. At Sabine Pass in coastal Louisiana, the oldest operational liquefaction terminal in the US, as well as the largest, there are currently 6 separate functional trains. The first 5 cost, as estimated by Cheniere Energy, which owns and operates the facility, between $17.5 and $18.5 billion to build, while the 6th added later cost of about $2.5 billion. After trains, the product is then stored, awaiting a ship. At Sabine Pass, LNG is stored in 5 separate tanks.
It is really cool that they actually cool the gas down to be liquid, I guess pun intended. It is interesting to think about how this is a standard process that occurs, that making something that cold makes it worthwhile to do, especially as they highlighted it goes from like 1 to 100x when you go back to the gas state. So that's very incredible that that actually happens on a regular basis. Again, I wish we talked about that more when we were referencing the US market and why we wouldn't have considered that here. Maybe there's more danger in having something that cold if basically that interacted with something else. Maybe it's both cold and it could also explode or be more dangerous. They didn't really cover those trade-offs here, which I feel like would have been useful, and especially in comparison to why they didn't reference any of this practice domestically.
Capable of holding an absurd 500 million cubic meters worth of gas. Once a ship has been positioned in a vessel berth, of which Sabine Pass has 3, and once the ship's tanks have been cleaned and prepared to take on the freezing liquid, loading arms are then bolted onto the ship and the filling process begins while crew members monitor ice buildup on the adjoining pipes. If the ship's tanks have already been cooled, filling will take about 15 hours. This process needs to be fairly quick, as Cheniere reported that it filled 423 cargoes in 2022 and 425 in 2023. Once the liquid natural gas is on the move, it's now the job of tanker operators to monitor its freezing cargo and minimize loss on account of off-boiling. There are 2 main categories of LNG tankers: those with independent tanks, like the recognizable Moss style with its spherical tanks, and those with the less distinguishable integral tanks, where the tank functions as a part of the hull. The former is older, deals with less sloshing, a danger that can damage tanks or increase boil-off inside the tank, and is reliably safe on account of the tank's isolation from the hull. The latter is capable of carrying far more, and because of this are becoming more prevalent, and are reliably safe on account of the tank's pliability should the hull be struck. But both rely less on continuously cooling their product than just keeping it cold in the first place, as both tank structures are maximally insulated with more than 20 centimeters of foam and multiple barriers surrounding the tanks. Still, some boil-off is bound to occur, but rather smartly, that's what powers the boat. And should the tank experience too much boil-off,
that is actually really smart. So they assume some loss of the gas, and then they actually use that gas to run the boat. That's actually very smart.
There are systems in place to slow the process, whether by running gas back through reliquefaction or by cooling the tank by spraying liquid from the bottom of the tank in the gap at the top. Keeping an eye on all of this is a crew of about 20 to 29 members, with at least 1 cargo engineer focused on the composition of gas within the tanks specifically. Upon reaching its port of call, the process is effectively reversed in a similarly labor and infrastructure-intensive process with regasification equipment in place of trains. Ultimately, for as dispersed as users of natural gas are, and diverse the uses of natural gas are, the process of making, moving, and regassing LNG is remarkably confined. Across the world's 2 largest LNG producers, LNG exporting is confined to only 7 active locations, 6 in the US and just 1 in Qatar. And as for imports, Japan, with the longest history of LNG reliance, is home to around just 30 regasification plants. But like all fossil fuels, demand for natural gas is expected to soon peak. New buildings are increasingly being built with heat pumps, electric water heaters, induction stovetops, and other cleaner, more efficient electric alternatives. In fact, already in New York City, for example, certain new buildings are banned from adding natural gas hookups. So this incredible network of pipelines and tankers will grow increasingly irrelevant in the coming decades. For now, though, it's one of the world's most fascinating interconnected distribution systems.
Well, that was pretty interesting. Thank you for watching. If you've enjoyed what you've seen, please hit like or subscribe. I will see you around.